In this lecture, we're going to introduce what are called the standard normal tables, and we'll have an introductory look at how we use them for analyzing normal distributions. So the standardized normal probability density function, it's a little bit of a mouthful. And we've met this function in the previous lecture. It's quite complicated, as you can see. And if we're to try and use this function for all the different scenarios like that we discussed in the first lecture, or any scenario that's governed by a normal distribution, the maths is very difficult. It's very easy to make a mistake, as you can imagine. So there must be a better way, and there is. Thankfully, mathematicians have gone out and made our life a little bit easier, but it does require a little bit of explanation as to what's going on. Main thing though, remember this function is what gives us our curve, our bell-shaped curve, but it's governed primarily by the standard deviation and the mean of the data set that we're examining. So to overcome this kind of mathematical problem, the standardized normal probability density function was developed. And what this function did was introduce the concept called a z-score. And a z-score assumes, first of all, that the mean is 0 and that the standard deviation is 1. And what the z-score really does is it counts how many standard deviations are we from the mean. So when you see a z-score and a number, that number represents how many standard deviations our value of interest is away from the mean. So don't be put off by the z-score. It's quite a simple concept, but kind of a complicated basis. So this allows for any mean and standard deviation values to be standardized. And now one set of tables was developed. So rather than kind of having to do that unique calculation for each unique mean and unique standard deviation, we can kind of bring our values to this standardized version with a mean of 0, standard deviation of 1. And then there's tables readily available that allows us read, well, what's the probability of our value of interest being here, there, or anywhere within that range. Main thing is though, it helps us avoid all the tedious calculations that would be needed. So the z-score is given by the formulas below, depending on what you call the mean. This is one version of it. X is the value of interest, x bar is the mean, sigma is our standard deviation. Or alternatively, we can use mu. Again, x is the value of interest and sigma. So it's pretty much the same formula, just with different representations of the mean. So this now is our standardized formula. Again, guys, don't worry, you don't have to use this, but it's just a lot simpler to use than the previous one. Here's our standard deviation of 1. Our mean is 0, and this gives us this much more simplified version. And then the tables were built off of this version. Again, don't worry, we don't have to use this, we just use the tables. So as I said, the mean is 0, standard deviation is 1. This gives rise to the normal standardized curve. This is it here. So here's our mean. This line represents one standard deviation above the mean. Now that would have a z-score of 1. Here we have 2. That would be a z-score of 2. Here we are 3 standard deviations above the mean, and that would have a z-score of 3. Similarly, if we went down the way, this would be -1 standard deviation from the mean. -2 or -3 standard deviations. So that's what the z-score does. It tells you how many standard deviations is your value of interest, because we might pick a value here. And then we can work out, what's the probability of a person falling into this bit or whatever. But we'll take a look as we move along. I don't want to get too caught up in examples just yet. So that's what the z-score tells us. How many standard deviations are we away from the mean? So this is the curve, standardized curve. The mean is technically 0. And here are the tables. Now, down here is the z-scores. So here's a z-score of 1. And we can count out then, so we could count out a z-score of 1.5 would be here. Now, just to try and explain what that means, just say if we said this was 1.5, what that figure 0.8531 would suggest is that 85.31% of the population lie to the left of that value. Just a couple of things to note. First of all, we start at 0 and 0.5. I'll explain that in a little bit. The table goes on then and goes up as far as pretty much 3.49. So this table actually just lists from a z-score of 1. I'll talk about it here. The tables only offer a z-score from 0 to just below 3.5 standard deviations from the mean. So it's only given us information. There's 0, there's 3.5. So the tables actually don't give us any information about the left-hand side of the curve here. This is the only place we have information from. That's where the tables give us. But if we're interested in an area to the left of the mean, we can use the symmetry of the curve to do our analysis. And we'll see this in later examples. If we have a negative z-score, what happens? We'll take a look. Because just going back to the tables, these tables, now there is other tables that give you the whole lot, but they're twice as long for obvious reasons, and they have pretty much the exact same figures in them. But these tables only give us positive z-scores between 0 and 3.5. So it just requires a little bit of skill and manipulation to try and figure out any information that's happening on this side of the curve. Any values below the mean, if we're interested in those, we just have to employ a little bit of analysis. So this is just saying, like, I don't, just what I pretty much said. And we will be doing that in this lecture, looking at negative z-scores. So once we know the mean and the standard deviation of a normally distributed dataset, we can examine any value of interest x using our z-score function. So in any question, you will always be given the mean, the standard deviation, and you will be told that it is normally distributed, which gives you license to use the z-score and to use the tables. The z-score, as I said, tells us how many standard deviations our value of interest x is from the mean. And we can then use the z-score to access the tables to determine the probability of x. And this step then saves us from all those nasty calculations. So the tables tell us, like I was saying, just with the 85.31, what those tables are telling us is that shaded area. A good tip for the tables is the tables will always tell you the biggest part of the curve. So we're going to do these problems, I would always insist that you sketch a curve, mark in your value x, and then it's going to be very obvious looking at that curve which is bigger? Is the shaded area bigger or the unshaded area bigger? It should be quite obvious that the shaded area is bigger. The tables will always give you the bigger value. They're always greater than 0.5. A z-score of 0 gives a probability of 0.5, and then the z-scores go up and this value goes up accordingly. It's a bit tricky when I don't, if we're not, once we start working through examples, I hope the logic of what I'm saying will make a little bit more sense. So we're going to take a look at a worked example, and we briefly looked at this in the first lecture where we had a maths exam taken by 100 students, has a mean of 50 marks and a standard deviation of 10 marks. And we were using the general rule then of standard deviations that, well, if we go out one standard deviation, we would expect 68 students to fall. Here's the mean of 50. One standard deviation would look like this, above and below the mean. And from the last lecture, we know that we would expect 68 students to fall in there. If we go to 2 standard deviations, well, then that entire area would be 95%. So that's the entire shaded area, just to be clear. Or 95 students in this case. And if we went to 3 standard deviations, above and below the mean, that would encompass 99.7% of our students. But that's very limited because it only allows us to go in very defined gradients from the mean. In other words, we can only jump one standard deviation above or below the mean, which is very limited really. We need something more robust and more versatile. So how many students would be expected to score higher than 75 marks? Very quickly, I always draw a curve, and I always expect you guys, for every problem, every part of every problem, you need to sketch a curve and show the value. So there's our mean. We don't need to mark in the standard deviations. We're interested in 75. And the question is asking us how many students would be expected to score higher than 75. So this is the area of interest. Now the tables will always give us the biggest part. So the tables are going to return that value. So we'll just take a look at this in a more formal sense. Draw a normal distribution curve, label the mean at the center, and only 3 standard deviations to the left and right as below. So sorry, there's our curve. There's x, that's what we're interested in. Mark in your mean always in the middle. And shade in the area of interest. So like I was saying, so if we're interested in the area above the curve, above x, how many students scored more than x, more than 75, that's what we're interested in, that shaded area. If we're asked how many students scored less than 75, then we would shade in the big area. So that's a really important part of these problems, is shading in the area that you're interested in and then interpreting the tables appropriately. So if we're asked to determine the population above the value of interest, the tables, like I said, they're nearly always given to the left, especially the tables we use, will always give us the area to the left of the value of interest, because that area is always going to be bigger than 0.5. So the unshaded area represents the area of interest we're interested in. And how we get this, guys, is very simple. Say, like I was saying, if we were looking at, say this figure here was 0.8531. Remember, the total area under the curve is 1, so the unshaded area is simply 1 minus 8531. And we can work that out then. So and that gives us 0.1429. So essentially 14.3% of the population lie above X, and 85. Oh, sorry, that's 6.9. I was thinking there was a mistake there. 6.9. So 14.7% live here, above X, and the tables would have read us the value of 85.3%. So it's really important to draw that little diagram and determine what area is the question looking for. This is just saying then what we do. We take, if our area is to the right of the value of interest, we simply take the value from the given in the tables from 1, and that determines the unshaded area. So we take a look at the question. Here's our curve. There's our standard deviation at 50. Sorry, not our standard deviation, our mean of 50, forgive me. That always sits in the middle. And we're interested in, well, how many students scored more than 75? So this is the X value from the Z score. So this is the portion we want, and this is what the tables will give us. But the first thing we need to do is use our Z score to calculate. We need the Z score so that we can go to the tables. And when we're looking at the Z score, we're really asking, well, how many standard deviations am I from the mean? Well, there's one standard deviation, there's another one, and there's a half. So just visually I can see 75 is 2.5 standard deviations from the mean. But we use the formula to determine that because it's not always as readily obvious as the way I've just done it. So use our mean and standard deviation. The question will always tell you these. The value of interest is 75. And then we use our formula. If your Z score is negative, just look up the positive value. Remove the negative sign, look up the positive value. But we'll see this in the next example, so we won't worry about that too much at the moment. So our Z score in this case, I think I have it on the next slide. I don't need to write it all out. So X is 75, mu, the mean, is 50, sigma is 10. Feed these values in, and we get a Z score of 2.5. So we know our value of interest. I have to keep emphasizing this, guys, so you understand what the Z score is. Our value of interest is 2.5 standard deviations above the mean. Now we go and we look up our tables. So we must interpret the QA. So the tables aren't going to give you the answer. Your sketch will tell you. So this is what we're looking for, our shaded area. The reason why we're interested in that little area, because the question asks how many students scored more than 75. If they asked how many scored less than 75, well then we'd be looking for the unshaded area in my little diagram there. And this diagram here, guys, when I say I'm looking for a diagram, that's all I'm looking for. A quick sketch. Don't make it hump shaped like this. It's a bell shaped curve, so you will lose marks if you just draw something like this. That's not a normal distribution. Normal distribution is bell shaped. So practice them and make sure your curve looks some way decent, because if you don't draw a nice curve, you're not going to get nice marks. Keep that in mind. So we go to our tables. Remember, we were from the previous slide. We're looking for a Z score of 2.5. I just had to split the tables in two. They come in one sheet, but just in order to make them readable, I had to split them into two. So 2.5 there. Now, if we were looking for, say, a Z score of 2.56 or whatever, we just move along. These are the next decimal places: 2.50, 2.51, 2.52, 2.53. And usually it's written up here, but like I said, I had to split the tables so the information isn't available just on this slide. Moodle has the full tables and you can just read them directly. So the tables tell us 99.38. Now what does that mean? I hope it's obvious that the biggest area, that must be 99.38, which would then suggest that the area of interest is 1 minus that, which is 0.062. So that's the probability of a student scoring more than 75 in this maths exam. There was 100 students who took the exam, so we multiply the probability by 100 and we get 0. So there's a little bit more than a 0.5% chance. So how do we interpret that? So that would approximately equal one student. Sorry, this is 0.62%. This is our probability. This is our relative probability. When we multiply this by 100, we'll end up with just about, 1%. We'd multiply this by 100. So it's written as a percentage, or so we're just kind of saying one student, and then maybe, might not be. So that's the answer to the first one. How many students would be expected to score higher than 75 marks? Really, actually this answer here, I shouldn't really have the percentage in there. It is correct in its own way, but not in the context of this. It would be 0.62 of a student would be expected to score more than 75 marks. So that's why I have the question mark. Is that one student? Maybe. If we round up, it is. So now we're going to take a look at, well, what happens if we get a negative z-score, minus 1.5 or something like that? Because the tables don't read. There's no negative z-scores in our tables. All this means is the value of interest x is lower than the mean. This is a graph of what we're talking about. And this might be a shaded area. How many students scored less than 30% in the exam? We're going to take a look at how many students scored less than 40%. Here's our shaded area. So what you do is you simply ignore the minus sign on your z-score and look up the tables as before. So I just have it laid out here. Look up the positive z-score. Sorry, I didn't realize shouldn't say log tables, into tables. And determine, these tables used to be in the old log tables. That's why I had it in there. So we look up the positive z-score and determine the value from the tables as before. So this is what we would usually get. So remember, this is what we're interested in. When we look up the positive z-score, this is what the tables will give us, the blue shaded area. Now, because of symmetry, this area here is the exact same area as the area we were interested in on the previous slides. So we take this value, so we want to find this, So we want to find this unshaded area. The tables will return this value, the probability of x. So we want to figure out the unshaded area, which is 1 minus px. That's just the probability of x. And then, because of symmetry, as I said, this area is the same as the area of interest from 2 slides ago. So that's all I'm saying there, is just going back. That area here is the exact same as our area of interest here. So we'll take a look at our maths example again. How many students would be expected to fail the maths exam? In other words, score less than 40. Here's our curve. This is your little sketch. What are we interested in? Well, first of all, always mark your mean. And again, when you're drawing a curve, guys, you don't need to label the bottom the way I have. You just need to mark in your mean and then have a rough guide. 40 is, well, it's really one standard deviation away. So that's a perfectly good curve. And then shade in our area of interest is this area here. So now we go to find, well, how many z-scores are we from the mean? I hope you'll see we're one z-score, but we'll work it out. So z-score is, -1. And like I said, if you go to the tables and try and look up a negative z-score, there is no negative values. So we just ignore the minus sign temporarily. Do shade in the area of interest, because that's what we want to know, how many students scored less than 40. Or to be more general, what's the probability of a randomly selected student scoring less than 40 in the exam? That's just to put it in a probability context. We go to our tables. I've just cut out the bit of interest, and we're interested in the positive. So we ignore the minus sign, turn it positive, and we look up the tables and we get 0.8431. Now the easiest thing to do is really just say, well, the tables always give me the biggest area. So that must be what the tables are giving me. So then my value of interest is 1 minus. Here it is, written all a bit neater. When we subtract 1 minus this, 1 minus 0.8413, we get an answer of 0.1587. Now there's 100 students. That's the probability of a student scoring less than 40. There's 100 students in total. So multiply this value by 100. 15.9% probability, or when we multiply by the number of students, it's approximately 16 students will fail the exam. So quick summary of the technique. The total area under the curve is 1. The tables give us the probability for z-scores, where they're standardized, mean is 0, sigma is 1. And we use z-scores to access these tables. Always sketch a diagram. If your answers, guys, don't have a diagram, you're not going to get a huge amount of marks, because the way I teach this, you need to have the diagram to interpret what the tables are telling you. If you don't have a diagram, you're in very sketchy waters. And you can see a small error if you forget to take away from 1. Instead of 16 students fail in the maths exam, we could very easily say 84 students have failed the maths exam, which might say a lot about your maths teacher or about your lack of following the rules. So read the question carefully, shade in the area you want on your little diagram. If the shaded area is more than half, you can read the probability directly from the table. If it's less than half, you need to subtract this probability value from 1, just like we did in these examples. If your z-score is negative, you just look up the positive value, but interpreting your diagram is always the same. So this is why when you look at textbooks, guys, they don't really insist on diagrams, and they get very convoluted about subtracting from 1 and not subtracting from 1. If you have a diagram, the diagram is giving you a very clear picture of what you're interested in, and then it's simply a case of you interpreting the tables from there. So we'll finish up here for this lecture. Just I don't want them to go on forever because it's quite a complex topic. It's taken me quite a long time to prepare these notes. In the next lecture, guys, we're going to ask, well, what's the probability of a student falling in between two particular values? That's another question we could ask. Say, what's the probability of a student scoring between 40 and 75? We've worked both of these, so we could work that out, but if we haven't got the previous values, it takes a little bit of interpretation. And then the next question, which is very important, is, well, if I want to be in the top 10% of my class, what score, what X value, what score in the maths exam do I need to get? And that requires a complete kind of turnaround of things. We have to kind of reverse engineer the whole process, where we're actually starting with the answer, 10%, and working our way back to find X. What score would I need to get higher than in the maths exam in order to ensure that I am in that top 10%? So that's what we'll be looking at in the next lecture, guys. Thanks again for watching. I hope it made sense. Yeah. Take care. Chat to you soon.